Ladies and gentlemen, welcome back to lesson 19 in group theory. In this lesson, we're going to continue our journey through the isomorphism theorems, going with the second isomorphism theorem, or alternatively, the diamond isomorphism theorem. The statement says that the isomorphism is in between the quotient group ABB and the quotient group A intersecting B. The simplest way to remember this is by drawing the lattice starting with the group G, and then the subgroup AB, the subgroup A and B of AB, the subgroup A intersecting B of AB, and lastly, the trivial subgroup containing only the identity element. Now, the reason it's a diamond is because if you trace the shape here, it's simply a diamond, and you see that if you take the quotient here, ABB, it's isomorphic to the quotient A intersecting B. So you can sort of see there's a parallel thing going on here. So let's get to it. Let us now officially state the second isomorphism theorem. Let G be a group. Let A and B be two subgroups of G, such that A is a subgroup of the normalizer of B in G. Then we have the following results. AB is a subgroup of G. B is a normal subgroup of G. A intersecting B is a normal subgroup of A. And lastly, and most importantly, the isomorphism that we've talked about. To make this easier to remember, notice that all three conditions here are very, very necessary in order to achieve the isomorphism here. First of all, we need to have that all of these things here are groups. And so we need to have that AB is a subgroup of G. And that's why the first result is important. The second result says that B is a normal subgroup of G, which is very, very important if you want to say that the quotient group ABB is a group. And similarly, for A intersecting B, we want to say that A quotient with A intersecting B is a group. So that means this has to be a normal subgroup. So that's why we need all three conditions in order to hope to achieve the last result. Remember that the theorem requires that A is a normal subgroup of the normalizer of B. So if we look at two particular cases, we'll find that this is true no matter the choice of the subgroup A. The first is when G is abelian, because when it's abelian, every subgroup is a normal subgroup, including B. So if B is a normal subgroup, then the normalizer of B is the entirety of G, and A, of course, is a subgroup of G. So it is a subgroup of the normalizer, and this condition is automatically met. The second particular case is that if B is a normal subgroup of G, then the normalizer of B is going to be equal to the entirety of G, and again, A is a subgroup of that. So with that in mind, let's get down to the proof. The first thing we'll prove is that AB is a subgroup of G. We will prove this using the two criteria of a subgroup. First of all, AB is not an empty set because, as we've said in the lesson of composite set, since the identity is in A and the identity is in B, then this means that the identity is in the composite set AB. So AB is not an empty set. The second one is that if we let A1, B1, A2, B2 be two elements in AB, then we have that A1, B1 times A2, B2 inverse is equal to A1, B1, B2 inverse, A2 inverse. And this here now, we will use a certain manipulation by multiplying this equation by A2 inverse A2. And you will see now why I did this in a second. And now we can see here that because of that, if we group the elements like this, we will see something nice. Here, this is an element in A because A is a subgroup, and this here is an element in B. But why is that? Well, because B1, B2 inverse is an element in B, so let's break this down into steps. This is A2, B, A2 inverse for some B in B. This is because B is a subgroup. And now, because A2 and A2 inverse is in the normalizer of B, then if we take the conjugate of B by A2, we need to get back an element inside B, because this is the definition of what a normalizer is. It's that the conjugate, it's still inside the set B. So this is an element in B. So we just have an element in A times an element in B. So this means this whole element is in AB. We've just succeeded in proving that AB is a subgroup. Completing the first part of the proof. We would like to prove now that B is a normal subgroup of AB. To do that, recall that a normal subgroup is closed under conjugates. So this is exactly what we'll be calculating, the conjugate of an element B1 in B by some element AB in AB. We have that the conjugate looks like this. We take the element here B1, multiply it on the left by AB, multiply it on the right by the inverse of AB, and this equals to AB, B1, B inverse, and A inverse. Now, B, B1, B inverse is all equal to some B2 in B. Because B is a subgroup, so it's closed under operations and inverses. So we will use the similar argument here because A is an element in A, which is inside the normalizer. So we have that A, B2, A inverse must be an element in B because A is in the normalizer. And so this means that it is closed under conjugates. B is a normal subgroup of AB. It goes without saying that B is already a subgroup of AB because B is a subgroup of the entire group G. This completes the second part of the proof. Let us now prove the third part, which says that A intersecting B is a normal subgroup of A. So let X be some element in A intersecting B, and let A be some element in A. We would like to prove the same thing we've already proven for number 2, but now for this subgroup. So let's take the conjugate A, X, A inverse, and we would like to see that this conjugate is inside the subgroup A intersecting B. So you want to see it's inside A and that it's inside B. It's inside A, obviously, since A is a subgroup and A is in A inverse is in A, and X is in A, because already X is in A and B, so in particular it's in A. And now we want to see that A, X, A inverse is in B. But since X is in B, and again, A is in A, which is in the normalizer of B, we have that AX, A inverse is an element of B. This means that AX, A inverse is in the intersection of A and B, and so the intersection of A and B is a normal subgroup of A, completing the third part of the proof. Now that we have proven all the preliminary results, it's time to prove the isomorphism itself. Now we consider the map phi taking an element from A, giving an element in AB/B. This might seem like an artificial choice for phi, like where did this come from? But then I will explain exactly how to think in a way that you will reach an isomorphism. Now, phi is defined to be taking an element A in A and giving us a coset AB in this quotient group. This is a quotient group because we've just proven that B is a normal subgroup of AB. So this is a quotient group. Now, phi is well defined. This is very obvious because B is a normal subgroup of AB, and we have that A is in A, implying that the coset AB is an element in ABB. In other words, if we take a coset AB, we're not going to be outside the group, the subgroup AB. We're going to always be taking an element in AB times B. So it is very well defined as a map. Next, we have that phi is a homomorphism. The reason it's a homomorphism is that if we take phi of a product of A1 and A2 in A, this is equal to, by definition of phi, A1, A2, B, exactly just using the definition here. And this, by coset multiplication, equals A1B times A2B. But this is just the definition of phi applied to A1 and to A2 separately. Very straightforward stuff here. We want to show that phi is surjective. And the thing that this does here is that it tells us that the image of phi is exactly equal to the codomain, which is the quotient group ABB. So it tells us that the image of phi is equal to ABB. Phi is surjective because if we let any element in the codomain, this is K, an element in ABB, then K is going to be equal to some element AB in AB times the set B. So this is just some random coset in ABB for some A and B in G. Note that ABB is just equal to AB because essentially B times any element in B gives B itself, because B is a subgroup. It is closed under the group operation. So AB here is exactly the image of A by phi. So it is phi of A. And phi of A is in fact inside the image of phi. So this means that any element in the codomain is inside the image of phi. That means that phi is surjective. Now we want to study the kernel of phi. What is the kernel of phi? Note that phi is not injective here, not necessarily. So we would like to know what is the kernel so that we can use the first isomorphism theorem that we studied last lesson and collapse everything into the kernel using this theorem and then saying there is an isomorphism. So even though phi is not injective, we would still like to study what is the kernel of phi. So A is an element of the kernel of phi if and only if phi of A is the identity. But what is the identity in this quotient group? Well, the identity is only when A is equal to the identity. So it's just 1B, which is B. Okay? But this just means that if we work on the left side, this is equal to AB, and the right side is still B. And this just means that A is an element of B. And because A is an element in A, why is that? Because the domain is taken to be all the elements in A. So already we know that A is in A. And now A is in B, so this means that A is in the intersection of A and B. So here, this is because A is already in A. So we've seen here that A is in the kernel of phi if and only if A is in the intersection, giving us that the kernel of phi as a set is exactly equal to A intersecting B. So this is the kernel of phi. So now, by the first isomorphism theorem, if we take our group A and we collapse it, we take the quotient group by the kernel of phi, we get that it is isomorphic to the image of phi. So we take the group A, we collapse by the kernel of phi, which is A intersecting B, and this is isomorphic to the image, which we've seen because phi is surjective, the image is equal to ABB. Giving us the desired result. Now, I still haven't forgotten to mention that the reason we took such a bizarre phi in the beginning is because we wanted to use the first isomorphism theorem. You can see the resemblance between this and that. All what we needed is to put this here and give us an isomorphism. So this is a very good practice. If you want to prove two groups are isomorphic, think about the quotient here and think, is it the kernel of some homomorphism that I can construct? If it's yes, then go ahead and construct this homomorphism, prove that it's well defined, prove that it's a homomorphism, see that the kernel is equal to A intersecting B, see that it's surjective, meaning the image is equal to ABB, and then use the first isomorphism theorem. Let us now look at an example for an application for the second isomorphism theorem. The example here is going to be in the group D16, the dihedral group of a polygon of 8 vertices, which is an octagon. So we have two subgroups of D16, A and B. A is given by the subgroup generated by S and R4. So basically generated by reflections and 4 rotations. B is a subgroup generated by R2, which is 2 rotations. We have that A is a subgroup of the normalizer of B and G, which is the entirety of G, because B is a normal subgroup of G. And I leave that verification to you as an exercise. Prove that B is a normal subgroup. Let us now try and use the second isomorphism theorem. Remember, the second isomorphism theorem says that AB quotient with B is isomorphic to A quotient with A intersecting B. So let us find out what AB is like. Okay, AB here is the subgroup generated by S and R2. And the reason is because if you explicitly write down AB, this is equal to all the elements A and all the elements B, such that A is in A and B is in B. And A here is going to be SR4, and B here is going to be R2. So after some verification, playing around with the elements, we find that they're all generated by S and R2. Now, the A intersecting B is just the elements that are generated by R4. So it's just 1 and R4. 2 elements. Now, AB quotient with B is simply putting these 2 groups together, and A quotient with A intersecting B is putting these 2 groups together. And the theorem says that, yes, we have an isomorphism between these 2. And in fact, this here can easily be verified to be isomorphic to the subgroup generated by S. And this isomorphism, I've done a similar one in the last lesson, the first isomorphism theorem, so I will leave that to you as an exercise so you can practice constructing these isomorphisms together. And with that, we have finished today's lesson. If you've enjoyed, drop a like, subscribe, and share with anyone who would be interested in this very nice topic. I'll see you all the next time. Have a nice day, and bye.